Hello and welcome back. Today I want to continue talking about the RF Class C amplifier by designing, building and testing such a circuit. I will be trying to apply and measure the things discussed in the previous video on the topic, so make sure to check that one out first. So if you're curious, then keep watching. First things first, what are the key specs of the circuit that I want to build? Well, I decided to go for a power of 0.5 watts into a 50 ohm load. So this should make it easy to measure using a termination resistor without breaking it. The Class C amplifier is narrowband, so the center frequency I have chosen is 3.65 MHz, which is the middle of the 80 meter band. Main reason being that it's quite easy to measure this frequency, and it will still be relatively immune to parasitics, compared to some larger frequency. As supply, I want to have around 10 volts, and the main amplifying transistor will be the 2N2219A. I had one of these lying around, so I decided to put it to good use. And obviously, while playing around with the circuit, I wasn't paying attention, so I broke the transistor. But fortunately, it's still being manufactured, so I could get a new one. So now, let's see what are the other components that we need other than our power transistor. So knowing that our input voltage is 10 volts, we know that our output voltage peak to peak will be double that of the input voltage, so our output RMS voltage will be the output peak to peak voltage divided by 2 times the square root of 2, which adds up to 7.07 volts. Now we need this value to work out what will be the load for which our LC circuit is being designed. So our virtual load will be our output RMS voltage squared divided by the output power, so 100 ohms. Now we won't be having the load connected between the collector and the supply voltage, rather it will be referenced to ground. So what we will need is also a DC blocking capacitor. Now with this capacitor and the load we have a high pass filter. So the high pass filter has a certain corner frequency defined by the resistor and the capacitor. And since the frequency at which we want to have our amplifier working is 3.65 MHz, we want this corner frequency to be at least 10 times smaller than our working frequency. So we want it to be below 365 kHz. Now, considering that our load is 100 ohms, if we take a standard value capacitor of 10 nanofarads, this will give us a corner frequency of 159 kHz. So we can go with only 10 nanofarads or also add some extra capacitance in parallel with it. But we cannot go lower than this value. Now regarding the other two components in our LC circuit, so we know our operating frequency, we know the Q factor that we want, so we want at least 10, and we know the load, so this virtual load is 100 ohms. So knowing these values and their attached formulas, we can extract our two unknown components, so the capacitor and the inductor. So we can work out that we will need a capacitor of 4.36 nanofarads and an inductor of 436 nanohenry. Finally, we don't want to drive an 100 ohm load, we want to drive a 50 ohm load. So we will need an impedance matching circuit. So I will be building a pi filter, so a two-stage matching circuit that will work as a high pass filter, so series inductor, parallel capacitor. So this will be built as a two-stage impedance matching network with an intermediate value of 10 ohms. And to work out our four components, we can use the spreadsheets I presented in a previous video on impedance matching. So I won't go into too many details on that, but knowing the various impedances, so input 100, output 50 and intermediate 10, we can work out that we need two capacitors, so 1308 picofarads, the other 1744 picofarads, and the total inductance, so the sum of these two individual inductors, 2.18 microhenries. So now we have all of the components we need for our Class C power amplifier. So I prepared this simulation with the various components that we've calculated, and I also added an RC network between the signal source and the transistor, so 100 nanofarads and 100 ohms. And just like last time, the input signal is variable, so it starts from 1 volt and it goes up to 2 volts using this parameter statement, which will be stepping the input voltage in 50 millivolt steps. And To assess the various inputs, I also prepared a set of measurement statements to observe the efficiency. So to see exactly what would be the ideal operating point. So if we run the simulation and we wait for the various runs to finish, we can now have a look in the error log. And here we can see that our efficiency peaks at around 84.7%. So pretty good for this type of amplifier. Now this happened in step 13, and we can also check the output power for step 13, which is 0.47 watts. Now it's slightly lower than the 0.5 watts that we were aiming for, but this has mainly to do with the fact that our transistor is not an ideal component. There are certain losses on it, so you can't really get exactly 0.5 watts. Now we can compensate for this by recalculating all of the components for a slightly higher output power, or by increasing the supply voltage a bit. But we'll leave things as they are for the moment. Next, let's have a look at this step 13 in a bit more detail. So I set the voltage of the input signal to 1.7 volts because this was giving us the highest efficiency in our previous simulation. So if we run the simulation, we can have a look at the various waveforms of the circuit. So first of all, we can look at the output voltage, see that it's nice and flat, there's no oscillations or any unwanted behavior, so this is good. Next, we can look at the conduction angle, so to have a look at the current in the collector of the transistor, and we can see that the transistor is conducting for about 100 nanoseconds, whereas the period of the signal is 275. So we're definitely below 180 degrees of conduction angle, so we're in class C operation. Another thing that we can check is the voltage in the collector of the transistor, and we can see that the peak of this voltage is roughly 19.7 volts. It's almost double the supply voltage, but we can also see that the minimum is 270 millivolts. So you're not getting to exactly 0 volts. That's because the transistor is not ideal. There will always be some voltage drop on it. Finally, we can check the amount of distortion, so to compare the collector voltage and the output voltage using an FFT spectrum. And although the output voltage is slightly smaller than the collector voltage, there's different impedance there, we can see that the harmonics are far better attenuated after the pi filter. So the circuit seems to be working. Now let's test it out in real life. Now, as far as the schematic goes, I added in most places multiple capacitors in parallel, just because the values that we've calculated are not really standard values, so I will be trying to get as close as possible to these using multiple capacitors in parallel. I also added an input filter, so just to prevent any sort of RF noise going out through the supply line, and I added various options to test out different things. So for example, I left space to put something in the emitter of the transistor, but I will be going with a 0 ohm resistor, and the base resistor can be connected through a jumper directly to ground, or it can be connected to an external offset to test out how this offset will influence the behavior of the circuit. Everything is finished off with a couple of RF connectors, so SMA input and output, and well, that's it. So I built this little board with the few components needed. The inductors are all hand wound with no magnetic core. The large one has a plastic support. I didn't use magnetic cores to reduce the risk of saturation or core loss. Also, regarding losses, the various capacitors on the RF path are all ceramic C0G or NPO type, so class 1 dielectric. Class 2 would be far more lossy and unpredictable. So let's fire this thing up. First thing to check is, does the circuit actually work? So for that I prepared the setup. So I'm using my power supply, which is off screen, to supply the board, and I'm measuring both the input current and the input voltage. So right now we can see that we have 10.2 volts, but no current. Then the input signal is coming from my signal generator. So this is outputting a 3.65 MHz signal into a 50 ohm load, and it's turned off at the moment. And then on the oscilloscope, I'm measuring the output of the amplifier into a 50 ohm load termination on the first channel. So right now, when there's no input signal, there's no current consumption and no output signal. So if we turn on the generator, we can see an output signal appearing, and there's a certain current consumption on the circuit. So we're using about 69 milliamps, and we're outputting a 4.5 volt RMS signal into a 50 ohm load. So the circuit seems to be working. Now we can play around with the input signal amplitude a bit, so we can see that the output is somewhat proportional to the input signal. So you can see that there is a link between the output and the input signal, but ideally what you want is to drive the amplifying transistor just a bit into saturation, so just on the tip of the input signal. So just to check this behavior, let's now look at what's in the collector of the amplifying transistor. So for this we can take advantage of the transistor case, which is directly tied to the collector. And what we can notice is that the voltage on the collector is reaching a maximum value of 18.4, so it's almost double that of the input signal. But we can also see that the minimum value is 1.6. So we're not fully saturating the transistor. There's quite large voltage drop on it when we are getting to the minimum voltage. So if we just increase a bit the input signal, we can see we're getting to lower minimum voltages, so 600 millivolts, and higher maximum voltages, 19.4. So you can clearly see the output of the C-class amplifier is double that of the supply voltage, in an ideal case at least. Now the ideal operating point, of course, will be adjusted based on the efficiency calculations, to which we'll get in just a moment. Now another thing that we can look at is the signal in the base. So we can see this upper half being limited, so this is when the transistor is actually conducting, and if we increase the amplitude of the input signal, we can see all sorts of distortions appearing. So this is not something that you necessarily want. You want to saturate the transistor, but only for a very little time period. And speaking of efficiency, even though the simulation was telling us that we should easily obtain more than 80%, if we run through the calculations with what we're actually achieving, so an RMS voltage of 4.57, input current 7.47 milliamps and 10.05 volts, we're only getting about a 55.6% efficiency on the amplifier, which is not that great. We can try to increase the input signal a bit, so to get a stronger saturation of the transistor. So this gives us a stronger output signal, but this starts to lower our efficiency. So now we're down to 54.2%. Now one of the reasons why we're getting such a low efficiency compared to what the simulation was telling us can be in the execution of the circuit and emitting some of the parasitic elements that the real components have. And another thing that can have an impact is the load that we're driving. So we don't just have the 50 ohm load, we also have the internal capacitance of the oscilloscope. Now one interesting thing that I noticed was that if I use a 20 decibel attenuator, we get slightly better results. So right now I added the attenuator, we have the same input voltage and current, but the output signal is now slightly larger, so now we're up to 5.01 volts RMS. And with this, we're getting an efficiency of 67% almost. So our initial measurement might have some issues with the final load. This way, with the resistive impedance matching, we might be getting closer to an ideal load. But anyway, now let's test another feature that seemed to have improved efficiency, at least in the simulator, and that is the applying of a negative bias to the base pull-down resistor. So right now this resistor is connected to ground, but we can apply a negative voltage potential to slightly decrease the conduction angle of the transistor and thus hopefully obtain a better efficiency. So now I removed the jumper that I previously had to connect the input resistor to ground, and instead I connected the second channel of the signal generator, which is set to output a negative voltage. So right now it's set to -1 volts to a 50 ohm load. So anyway, if we now turn on the first channel, we can see that nothing is happening. We obviously need a much larger input signal to get to drive the transistor because of the offset that we included. So if I start to increase the input signal, at some point we can see that current is starting to increase, the output signal is starting to appear. And right now we have an output signal similar to that which we had before, so 5.13 millivolts RMS, but our input current is only 68 milliamps. So this is giving us an efficiency of 76%. So by making a smaller conduction angle, we've made the circuit a bit more efficient. Now, you might be tempted to just increase the offset more and more to obtain better efficiencies, and follow that by an ever-increasing input signal voltage. But that is not always a good idea. There are two limits to keep in mind: maximum collector base voltage and maximum emitter base voltage, or equivalents for other types of transistors. So by adding the offset and increasing the input voltage, the base will be going to more and more negative voltages in reference to the emitter, and at some point you will exceed a limit. For this particular transistor, the collector base voltage limit is 75 volts, which is not that big of an issue, but the emitter base voltage is 6 volts. So if we get the base to a voltage lower than 6 volts in reference to the emitter, the junction will break. Now, moving on, I will be leaving the amplifier with the base resistor connected to ground, and we'll be looking at some of the other features of this type of amplifier. First off, frequency multiplication. So initially, if we're injecting a 3.65 MHz signal, we're getting a 3.65 MHz signal on the output, since this is the frequency around which all of the components were calculated. But now, let's try to insert a smaller frequency, so a frequency submultiple of 3.65. First off, 1.825. So by doing this, we can see that our output signal still has 3.65 MHz, it's just that it's not that uniform. So this is coming from the impact of the Q factor of the output circuit, of the circuit in the collector of the transistor. So we can see that after the first cycle, the signal is starting to decay, but we are getting a frequency multiple of our initial signal. We can of course take this one step further by using a third of the output frequency, so only 1.2167 MHz. And by doing this, again we still get the same output frequency, around 3.65 MHz, but we can see far more clearly the decay of the signal. So after we've injected a bit of energy into the LC oscillator, it starts to decay. Now of course you can get a very nice and clean frequency multiple by using a better filter, so by going for higher order filters. These will remove the various amplitude variations of the signal and will keep it nice and flat. But regardless, if you need to make frequency multiples in a simple way, the Class C amplifier is a good choice. Next, we can look at the output spectrum of the amplifier to see just how clean it is. For that I prepared the spectrum analyzer, so I'm using the same signal generator to inject the signal, but the output is going through the 20 decibel attenuator into the spectrum analyzer, which I've set to measure between 3.6 and 3.7 MHz, so the 3.65 is just in the middle, and the bandwidth is set to 100 Hz. So now if we turn on the input signal, we can see a very nice, very clear, sharp signal in the middle. We can see that the frequency of this thing is 3.65 MHz, so it's stable, it's sitting in one place, it's not moving around. And next, we can look at some of the harmonics, so to see at least the first upper harmonic of this frequency, 7.3 MHz. So now I increase the range from 3 MHz up to 10 MHz, and we can clearly see two spikes appearing. So our fundamental frequency at 3.65 and the first harmonic at 7.3. Now the exact amplitudes of these we can check using the marker function. So we have about -8 dBm on the fundamental and -60 dBm on the first harmonic. So of course if you need a cleaner output signal, you'll need to create a better output filter. So it's quite common to see in RF amplifiers multi-stage filters on the output, specifically to clean up any sort of harmonics that might be appearing there. Now the main use case of the Class C power amplifier is that of providing a constant amplitude waveform, either of constant frequency or of variable frequency. So it's quite useful for various frequency modulations, but not much else. So first, to check out this feature, the frequency modulation, I prepared a setup in which I'm supplying the circuit with a signal, and then I'm plotting the FFT spectrum of this signal. So we can see that we have our main peak at 3.65 MHz with a fixed amplitude, and then the device is picking up some other peaks from the noise floor. But if we also include some modulation to this input signal, so right now I have a half a hertz FM frequency with a deviation of 20 kHz. So you can nicely see on the FFT spectrum how the input signal is varying. So it's going around our center frequency of 3.65 MHz, plus 20 kHz to 3.67 and minus 20 kHz, 3.63. And all this time, the amplitude is staying constant. So even if it's not clear in the table, it's clear in the measured signal. So the amplitude of the measured signal is always staying constant. So as long as we're inside the bandwidth of the amplifier and the various matching circuitry, you can change the frequency and the amplitude will stay the same. Now, the type of modulation for which the Class C amplifier is not recommended is amplitude modulation. So first of all, even though there's some sort of link between the input and the output signal, it's highly unlinear, so it will cause a great deal of distortion. You can try to modulate the supply voltage, but that will also cause various problems. And the other aspect, other than distortion, is the speed at which the amplifier reacts. So to show this off, what I prepared here is an input signal which is modulated in the amplitude skip key modulation. And what this is doing is that it's providing pulses of radio frequency signal and then pauses. So we can see the input signal clearly here in blue. We've got pulses of signal and then pauses. Now, if we look at what's coming out of the amplifier, we can see that the output isn't really following the input. So let's just adjust things a bit. You can see that as soon as the input signal starts, the output takes a while to build up its amplitude, so the amplifier is not reacting very quickly. And in a similar fashion, when the input signal stops, well, the amplifier is still providing some signal for a while. So it's not very fast to react to changes in amplitude. In the end, even if the circuit does not work exactly as it was predicted in the simulator because of various differences that were not modeled, having the simulator at our side is always a useful tool to try to debug and reproduce real-life effects in a smoke-free environment. There are a lot of parameters that are very difficult to measure in real life, but are no issue in the simulator. And with that said, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and see you next time. Bye bye.